up again. All right, that is recording too, yeah? Okay, so today I want to wrap up what we've been talking about with point clouds and what I've been calling geometric view of perception. Okay, so just to recap a bit, we started off by talking about, let's say maybe day one, in addition to introducing point clouds and cameras and the like. We talked about the point registration problem, where you have 2 point clouds and you're trying to find the pose that maps one into the other. So that's a point set registration or point registration. We went from there into the iterative closest point algorithm. That snuck into day 2, but that was the start. And then day 2, we started addressing the fact that real point clouds are messy, right? We talked about the various ways that they could be messy. And we talked about generalizing the notion of correspondence as one way to address this, right? And things like more clever ways to deal with outliers, right? And we generally toyed around with generalizations of this point set registration problem. You know, we're trying to find, we've got 2 point clouds. We have to guess the correspondences or somehow be told the correspondences, but we're going to roughly try to register these 2 point clouds together. But I don't want to leave this sort of part of the course until I tell you that I don't think point set registration is sort of the only way to think about this. And it's not clear. We started talking about it a little bit at the end last time, that this idea that you should just find the pose that makes 2 point sets close together is always the best objective. It might be lacking in important ways. So today, I want to go beyond just registration and start thinking about some of the other aspects of what makes a good perception system. Just even if you're given just point cloud data, what are things that you need that maybe is beyond the metric which just says, are my points close together? Okay. And I can start with that, and this is still in the context of sort of geometric perception. Unfortunately, there's a lot to perception that's beyond geometry too. But even in the landscape of sort of geometry, I think there's things that are missing from our basic algorithms, and I want to start talking about them today. So here's what happens when you start using ICP and all these variants, right? You have a beautiful model of your mustard bottle or your coffee mug or something like this. It's sitting on the table. You've got a couple cameras pointing at it. And ICP tells you roughly that, here's the table, and it's like, here's my mug, and it's telling you that your mug is in the table, right? For instance, like it got some returns, it did its best bet to fit, and it's giving you a pose back that says, mug is in the table. I guarantee that'll happen. It'll happen for a bunch of different reasons, maybe because you have points down on the table that are pulling it down, or we have outliers or something like this. But this is a very classic thing to happen, is you're looking at it and you say, that's a silly answer. Clearly the mug's not in the table. Or you'll get another one where, the mug is floating in the air, right? And, again, something that the point set registration algorithm doesn't know, which is that mugs don't spontaneously hover in the air, right? I mean, maybe when they're in motion, but if the scene is static, then this shouldn't be a reasonable answer. And another one that you'll get often is if you're trying to register multiple things, it's sort of a version of this. You can get, if you're trying to register multiple mugs at the same time, you'll get them overlapping, for instance, right? It'll say, I found 2 mugs in the scene, for instance, and they're, in penetration. Okay, so there's clearly things that you know that we somehow haven't yet expressed in our points should be close in a Euclidean distance objective. Okay? There's another really clever one about just knowing that the camera, if the camera is getting point clouds here, or points here, and the camera is over here, right? Then you also know, for instance, that there can't be an object anywhere here between the camera and the points, right? We haven't captured that yet either. So the goal for today is to think about ways to capture those kind of events. Yeah. So I'll call the free space constraints. This would be, I guess, both this one and this being in the table. These are non-penetration constraints. And this one's actually interesting, right? This fact that mugs don't fly normally. This has to do with physics, right? It requires something about the equations of motion to know that that's not an okay solution. So in the case of a static scene, I think the simplest version of this would just be to say this is a static equilibrium constraint. Right? You somehow know that if you were to draw the forces for a free body diagram, those forces should balance and you should have equilibrium, right? And we haven't yet told our perception system how to think about that. Okay, so all of these are possible. Some of them are harder than others. But to do it, we're going to have to start. We're going to have to give up a little bit on the beauty of our formulation, right? When we were up here, we were solving this beautiful problem in the point set registration, right? We were solving this sort of a problem with some correspondences known, and we used primarily the singular value decomposition in our inner loop. Right? This was our heavy hitter, was the ability to, if I give you a bunch of 2 point clouds and I know the correspondences, then the inner loop could be, I can find that pose using singular value decomposition. And that's beautiful, and it always works. It'll you can give it noisy point clouds, it'll find the best effort, it'll solve this least squares problem. Okay, and every time you call it, it'll give you the same answer. It's good stuff. We're going to give up on that. We're going to have more approximate methods these days that will work sometimes, not always, but can handle a richer specification of problems. Okay, so I realized last time I went off the rails a little bit, this is why it's good to come to lecture even when the videos are online, because I saw all of you going like, what? Right? And that's feedback for me to know I went a little fast at the end. So let me just make sure I put this in context, right? What we've been talking about, some of these optimization problems, we've been talking about convex optimization problems. And the examples I gave you before were, for instance, when I had a quadratic objective, right? If I had, let's say, x1, x2, and I wanted to minimize over x something that looks like ax minus b squared, right? Subject to some linear constraints. You've been playing with this now as a quadratic program. Okay? So this is a beautiful type of optimization problem where I don't have to even worry too much about having an initial guess for x. All I need to do is find the minimum of this cost landscape, which satisfies these constraints, and I know that I found the optimal answer to the problem. This is just one example of the space of convex optimization problems, which we're going to use but not study in the depth that they're worth studying. But I think you can use them very effectively with just having this basic understanding of things that have quadratic objectives can be handed into a quadratic programming solver, for instance. If you had a linear objective but still linear constraints, that would be a linear program. Some of you have known about that. There's other examples, so linear programming is a really important class. LPs. You might hear second-order cone programming. This is LP. This is SOCP. And I mentioned too quickly last time semi-definite programming. Which is SDP. Okay. So there's these important classes of objective functions which look more interesting. They might look like ice cream cones instead of like a bowl, but they all have this property that if you write the problem down and you can fit it into one of these frameworks, then you are sure that your solver will be able to find a minima and give you the global answer. Okay? And we'll use some of them again as users throughout the class, but I want to mostly make a distinction between those and what we're going to start doing today, which is more general non-convex optimization. Okay. So now I'm going to think more generally about minimizing some function subject to some constraints. Right? I still have my objective function up here, my constraints down here, and my decision variable is x. But now when f is arbitrary, I've lost this beautiful picture, right? I can suddenly start having cost landscapes that are much more complicated. Maybe f is doing this. And the expectations we should have for the algorithm are therefore a little bit less, right? We're going to basically have algorithms that will say if I start from an initial guess, they'll find a minimum, right? Maybe I start from this initial guess and I'll walk down the hill, right? And it will return a point saying, this is the best I could find, right? Some minimum. We'll call this a local minimum. But in general, unless you know something more about the class of these curves, we lose the ability to say that I guarantee I found the best solution. Okay? So this is just a very high-level setup, but what I want you to make sure it lands is that the problem of registering two-point clouds, where objective is just this nice quadratic distance between the points, we were able to use strong convex optimization kind of ideas for that. When you start doing these other important things, which are obviously important to rule out non-sensible solutions, then we are almost always going to leave this picture and enter this picture. So you'll have perception systems that maybe don't stick the mug in the table, but they might give you they might not give you the best solution. How does that at that level? Are there questions at that level? I know some of you know this well, and some of you, that's a very fast introduction to a big topic, but I'm trying to walk that line. Yes?
How do we do it, like as humans? Are our senses better, or do we do all this like optimization?
That's a great question. So the question is, when humans are doing perception, what are we doing? Are our senses better or whatever? Of course, I don't know exactly the answer, but I think some things are clear. I think we are bringing so much extra information to bear on the problem, common sense type information, that changes the way we perceive the world in ways that these geometric algorithms are not capturing. And even deep learning algorithms are not capturing, although they're getting closer, right? I think as we start, using foundation models and large-scale models that really have some broader understanding of where objects can be in the world, then maybe there's hope for some common sense. But if I open a refrigerator, I have tons of priors about what I expect to see in the fridge and what I don't expect to see in the fridge, right? If there was, I don't know, a gorilla in my fridge, I would be surprised and my perception system would fail probably, right? At least in the short term, I would probably run, I don't know. But I think if you start reflecting on what you're doing as you're going through the world, before you open your eyes, you're bringing in so many initial guesses, right? Which then makes I think we probably don't have super accurate geometric reasoning. I mean, people are good at 3D reasoning, but not like depth camera, sub-millimeter accuracy kind of good. I think robots should be far superior than humans in terms of accuracy in those kind of computations. Okay, but I think certainly we are able to rule out silly cases. The computational machinery with which we do that is hard to know. Yeah. Yes? Okay, that's a huge question. I love it. Well, maybe so. The question was about tactile sensing and how. But let me bite off a version of that question, right? So how would a tactile sensor, for instance, fit into this? And since we're talking about point clouds and geometry, a particular type of tactile sensor that's very popular these days is when you actually put a camera underneath your finger, okay, or palm or something like this, and you actually can get a point cloud. It's a very special point cloud that never sees past your skin, for instance. But you can imagine actually using these tools almost out of the box with a tactile sensor also. Think of it as a camera that has a maximum range that is your skin. Okay, but of course, bringing in things like non-penetration becomes very important when you know immediately that things are going to be touching before you see them. So. So I think actually this lecture is very well motivated by tactile sensing. So why, I think you're right to continually press on why tactile sensors. I think tactile sensors have more potential than they have realized so far. I think everybody in the field would agree with that, but somehow we have massive data sets and a massive computer vision community and stuff like that, and we have like a few people making tactile sensors. A new one came out today, the GelSight Mini just came out today. If anybody saw that, that's cool. So maybe a new form factor, but they're just not as many. They're not in everybody's iPhones, right? It's a smaller scale. That community is still growing. Okay, good. So I want you to know actually that although there's a ton of things to know about these different problem classes, and when you go from non-convex to convex and things like this, when you're writing code, for instance, in mathematical program, or there's a handful of optimization parsers, which try to do some of the heavy lifting for you. Okay, so if you write in costs and constraints, in the language of mathematical program, you add cost, add constraint. Mathematical program is actually doing a lot of work behind the scenes to decide whether you've still stayed in the realm of a convex optimization, and when it can detect that you have, then it will call a special solver that's extremely efficient for convex optimization. When you add a more general constraint, then it'll bounce over to there's still custom solvers behind there that solve nonlinear problems, but they use a different set of algorithms behind the scenes. So, for instance, if you just in mathematical program, you add a quadratic cost, so it doesn't even have to guess at this point. It knows the objective is quadratic when you say add quadratic cost, okay? If you add a cost like this, actually, x dot x, where x is the decision variable, then because x is actually symbolic, it knows enough to be able to parse that and realize you've added a quadratic constraint, and it will call a QP solver. Similar, like those are the same here, okay? But you can also add arbitrary functions as costs or constraints, and we'll do that today, okay? Just define a Python function. And here, it doesn't have the ability anymore to know that even though this one happens to be quadratic, you could have put an arbitrary function behind there, so it sees that it's going to start calling a nonlinear optimization solver. And when it calls your function, actually, it's going to pass in a version of x, a variable that is an autodiff type, which is automatic differentiation, so that it can also take gradients of your function and try to use gradients of this in order to get down there as fast as possible. Yes?
I have a weird question. So far we look at a snapshot of the scene as a model, right?
Yeah.
But if I have a changing environment, I want to changingly adapt my perception of the model within the scenes, then maybe I have situations where the cup is in fact flying through the room.
Yep.
And given the constraints I have on my model, I wouldn't perceive the cup in that moment because it would be not a static equilibrium constraint, right?
That's a great point. So there's 2 points to there. So let me repeat the question. So let's say I'm not taking we've been talking mostly about you woke up, your eyes are open, the world was still. How do you understand it? And in that case, something like a static equilibrium constraint is appropriate. But the problem is actually different when things are moving. Both in 2 ways. I think first of all, if you open your eyes and admit things could have been moving when you started, then you don't want to be using static equilibrium constraints. You could use more general dynamic constraints. You know that things are not going to be, falling faster than the acceleration due to gravity, for instance. That could be a constraint on your perception system. There's also a separate part of that question, which is if I'm not opening my eyes and taking a one-shot sort of approach to it, but I'm rather tracking, then that can also change the problem. You can take an initial guess and expect that the answer only moved a little bit. And the same way we did, instead of inverse kinematics, we did differential inverse kinematics. You could start taking, just Jacobians of some of these things and expect actually a linearization of these problems to work fairly well. So I think in both ways, the tracking problem and the dynamic problem are pretty different. I'll mention tracking again at the end just to close that loop, but that's a very good point. Great. Okay, so let's think about first the problem we already know, but in a way that gets us into non-convex. Okay, so if I had parameterized my point registration problem, my point set registration problem, using theta instead of the pose written out with rotation matrices and the like, then already I have a non-convex formulation of the problem. So let me just say that carefully here. I think it's a good way to bridge to the more advanced versions here. If I wrote before, I was minimizing over P and R, where R was in SO3, right? Sum over I, P plus R. Oops, PSI. Okay, and I could write it like this, or I can write it with the R transpose equals I, right? Determinant of R equals +1. Now, by writing this and this, I feel that I've overspecified it, but at least it's super clear, okay? So the decision variables here were, this is a matrix now. R is a 3 by 3 matrix. This is a 3 by 1 vector, so I had 12 decision variables. Or in 2D, maybe it was a 2 by 2 matrix and a 2 by 1, okay, in 2D. So what if we instead said, I want to parameterize this by just minimizing over P, which is the 2 by 1, and theta, okay? And I'll write the same objective, but now I'll have theta enter through the rotation matrix like this, right? Where R theta is my standard cos theta minus sine theta, cos theta. Okay, so I've changed my decision variables. Instead of being from the matrix, the entries of the matrix R, to now being just one variable theta, right? This is just a scalar. That seems good. I've got less decision variables, maybe. But my beautiful quadratic bowls are not beautiful quadratic bowls anymore. I've got some sines and cosines in here that are changing it. In this simplest example, we can still think about what that landscape looks like. Okay, so let's do that. And just so I can draw it on the board, let's even do it with the rotation-only case first. I'll just say positions are known, or we maybe played our trick of using relative positions, so we did everything relative. So let's think about having our model. So we had an accident last time, and my blue chalk is no longer with us, so the model points are now green. Sorry for that. I had a nice thing going there, but let's take my non-symmetric shape. This is my model points in 2D. Okay. And I've got my scene points, which are going to be only rotation for now, because I've already subtracted out, because we know we can subtract that out. I've got my scene points like this. And the question is, what does the objective, if I plot a function of theta, what does this cost look like? And is it going to be terrible, or is it going to be sort of okay? And I think it's actually not that bad to draw. It takes kind of a thought experiment, but let's take any one of these points. This is with the known correspondences, this case, okay? So if I have my model point and my scene point, then my cost is the distance here. Okay? My rotation, they should be, if I had drawn it perfectly, they would lie on a circle, right? Because if they're only allowed to rotate, then those things are just going to move along a circle, right? Okay. So if I have an initial guess, then my claim is that actually this point here is going to contribute one cost term, which is the distance of that arc, right? The distance of that arc is going to be a function of my angle theta and the distance from the origin. Right? I can just use my standard cosine law of cosines to figure out what that is. If I know this length and I know this length are both some radius r, and I can write it as a function of this angle, I can tell you what that distance is. Right? It's going to be what is it? R squared plus r squared minus 2 r squared cosine theta. Should be the length of that distance. Let me make sure that checks. If theta is 0, so it's exactly the thing, that's 1, and this distance is 0. I'm pretty happy with that. It's close to that. Okay. And let's say that's the distance for the ith point. Okay. Now the sum of the distances is just going to be a sum of all these things added up. These are constants from the point of view of this optimization. I'm just optimizing theta. So I just have actually cosine theta times a big sum of 2ri squareds plus whatever this is, right? That's my cost landscape. Even though the shape is kind of interesting or whatever, in polar coordinates, it's actually really easy to write the cost landscape. So if I'm searching in this parameter space, it just looks like a cosine, roughly. Adding a constant will move it up and down. Adding a multiple like this will scale it up and down. But roughly, my cost landscape in 2D, reconstructing the orientation, looks like this. Okay? My claim is that and that's supposed to be a nice cosine, not a lumpy cosine, which is sort of important to the point I'm making here, right? So maybe I'll just make that a little lower so that those are the same, yeah? If I start a nonlinear optimization and its basic behavior is to go downhill until it finds a local minima, then in this setting, it's actually not bad, right? It might tell me something that's the angle I expected. It might tell me something that's 2 pi away from the angle I expected, but it's still right. It's not wrong. And the answer it gives me might depend on what my initial guess was, but it's actually going to solve that problem very nicely. In particular, there's a trendy way to say this, right? This function is non-convex, but all minima are global minima. So we like to try to say that about neural networks too. Okay? And there's other, I think this is a new trend, is understanding cost landscapes that have this property, that are not the simple picture, but they're somehow still good optimization problems. Okay? So all minima are global minima. Minima. So they achieve the same cost. So it's sort of not crazy if you're trying to, to parameterize 2D estimation problems in terms of theta. This is a little bit too rosy of a picture. In 3D, it's going to get more crazy. And when you have to search for the correspondences also, we know from ICP, or we should expect from ICP, that there are going to be cases where it can get stuck in local minima. So we'll see that happen too. But I want to establish that, out of the box, it's not terrible to think about trying to search directly over this kind of a parameterization. Okay, and these are the kind of tools that you have in non-convex optimization. Yes?
So I'm just trying to understand this RRI squared situation. What does that correspond to in terms of a circle?
Yeah. I just need one more color to make that. I was just trying to find a function to compute this distance, right? The distance between the point on the model and the point in the corresponding point in the scene. And my claim was that that's an easy thing to compute if I call this R, and I do it in polar coordinates. This is also going to be R, since it's just rotating around the origin. That's all I've given it the ability to do if I've subtracted out the means properly. And this is R, so then my math was just to compute this distance as a function of my rotation angle theta.
And then this sinusoid situation is you going through all the points, like the one corresponds.
Yeah. So good. So when I get the correct theta, my cost is 0. I've lined up all my points in the noise-free case. When I go all the way to the opposite side, I've got the biggest possible distance and my biggest possible error. But if I keep wrapping around 2 pi, then I'll get 0 error again.
Oh, I see. So it's a question.
In fact, I should have drawn this, stopping at the end. In fact, that would have been more insightful on my part. I didn't think of it that way. I just looked at it in the algebra and said I've got some constant, so it could be anywhere, but actually that should be 0. Right? It touches 0 when things line up perfectly. Good. I drew it with a 0 here. I forgot. Okay. I had that insight once, but. Okay, that's our toolbox. Now we want to start saying, okay, if that cost function isn't rich enough, or I could potentially use constraints, how do I want to change that in order to capture these more rich phenomena? So remember last time we talked about generalized correspondences, but we still did that in a 2-step optimization. So let me write that. So for instance, when we talked about the coherent point drift, CPD, last time, my claim was that it was minimizing over some pose, some function like this, right? And this was set as using a Gaussian kernel. In an iterative algorithm. Right? So the same way ICP set the correspondences based on minimum distance, and then and solved this problem. CPD was setting the correspondences to be soft correspondences using the Gaussian kernel, and then solving the SVD problem. Set it, solve the SVD problem, and alternate. The dream would be that we can solve for the correspondences and the poses at the same time. Now we have, if we're willing to go to the non-convex optimization, then we can do that. We can write that down. Our mileage may vary because there could be local minima, but we at least can write that down. So, today we can do that same sort of thing. In fact, the more general way to write this would be to say minimize. I could do it in terms of x, but maybe I'll minimize directly over theta now, for instance. And I could say for ij, let's take a nonlinear loss function. I'll be careful about this in a second. And maybe it's a function of the transform points. Still, let's keep that structure. Okay, but I restricted myself to just quadratic functions before. Now I'm going to have an arbitrary loss function. The quadratic form is best for optimization, maybe, but the arbitrary loss function allows us to capture things like outliers and other features. So here are some sort of standard choices. You might hear about Huber loss. Gaussian, you could use the Gaussian kernel. That's roughly what the CPD was doing, right? Which is nice because the idea from the Gaussian was that functions that are, points that are far away have no effect on your optimization. It's a little subtle. I drew this here the way that you would normally see it in terms of a loss function. The Gaussian doesn't go to 0 in the way I've drawn it, but it's still, because it's flat, it has no effect on the optimization. So points that are far out here, if you were to move your guess a little bit and move them from here to here, it doesn't change your cost. So even though in a cost landscape setting, you might shift yourself up or down because it doesn't go to 0, but it doesn't change the shape of the landscape. Okay. I'm saying something I think simple. I hope I didn't say it in a complicated way. It's just that we were a little restricted by this quadratic form before, and we had to do these games with the coefficients. The more general case is just write the function you wanted directly in the loss. Yeah. Any questions about that? Yeah.
So the in the equation, we need this quadratic looking thing, but we don't want the final loss of quadratic, and we need to multiply by strategic coefficients. Why is it exactly that we can't just keep moving in the operator?
We could have done this. So the question, maybe I'll try my answer. Hopefully it's clear from this. Why didn't we do this right from the get-go? This is certainly one instance of this. This is just a more general form. If I choose L to just be the quadratic form, it could just be take whatever's inside this function and square it and add, and multiply it by C. So this is a special case of this. This is a more general thing. And because it's more general, it can do things like taper off on the sides, which is a general way to handle outliers. That's the same way that we were handling outliers before. We now have machinery that'll handle outliers like this.
I see. And every single CIJ is literally just a scalar that follows some sort of Gaussian-looking thing, and it just basically modulates.
Yep. Before, what we were doing was we were taking the losses we got from corresponding points. If the points were very unlikely to be corresponding, we were making that loss effectively 0. Here, in the same way, we're saying if the points are too far away with let's say the Gaussian loss, if they're too far away, we're saying it has no effect on my cost. It's a flat. It's not quite 0, but it's flat. So it has no effect on the shape of my cost.
And the last question is, those points that are really far away, are those points that are extremely long in this rotation, or are
Yeah. So those points that are far away are given our current guess. This is always going to be based on your initial guess. You're saying that my model here is here, my scene is here. I'm going to give no weight to the difference between, I'm not going to worry about trying to make this one match this one. That one's just too far away to worry about. I'll worry about the points that are closer, where my model to scene is smaller. Yeah. I had a request just to convince everybody that I do read all the surveys. I really do. Not many of you write that much of the surveys. You tell me how many hours it takes, which is a little bit high this time. But you also, a few of you write comments, and I read them all. And someone asked for a stretch break. All right, so let's take like 2 seconds to just stand up and stretch. Yeah, it's a good time for it. You have to listen better now. Sure, good. All right. They also said it could be small. They just was like, I just want to stretch my legs. So we're back at it. That's it. Okay. There's a bunch of things to know about sort of writing loss functions and writing code that uses these kind of loss functions, right? So, in particular, when we were operating on this Euclidean distance a lot, I mentioned that there's data structures that are really good for that. Right, so if you want to just find nearest neighbors in some Euclidean distance sense, a natural data structure is to use KD trees or other data structures you've learned from computer science classes, okay? Just to be efficient nearest neighbors. Efficient nearest neighbor. When you get into these more general loss functions that are functions of distances, there are other clever tricks. One of the ones that I like best is actually to use these sign distance functions. Okay, it depends on exactly what thing you're computing, but a common data structure that's useful to make these things fast SDF. Not the scene description format. It's a different SDF. There's too many of them flying around. Okay. So the sign distance field or function, again, Stanford Bunny comes up often. Okay, you can pre-compute. If I have let's say a mesh, and I want to compute what is the distance, the closest distance from any point in the space to that mesh. And if I'm going to be doing a lot of queries that's just asking what is the distance from a point to the mesh, then an efficient algorithm will, for instance, just pre-compute on a grid all of the distances from points in space to the mesh. Okay, they'll throw that on a GPU and then be able to access that super fast to do lots and lots of point queries, lots of distance computations on these 3D objects. The sign distance function, it's signed because you have a positive distance when you're outside the mesh and a negative distance when you're inside the mesh, because it's important to distinguish those two. Yeah? Okay, and 0 when you're on the boundary. It's just another representation of geometry, but it happens to make these distance-based objectives and queries very efficient. Yes?
So is that pre-computed on the model or in the scene?
Yeah, that's a good question. So the way I've written it here, you're going to move the model every time because as you change the decision variables. But remember I said you could have also done everything like this, OW, PSI. So the question was which one are you going to pre-compute the sign distance function for? Typically you have a model that you can afford to pre-compute with, and the scene comes in every time, right? So it makes sense to try to do your pre-computation on the model, not the scene. And if you were to flip over to this representation where you're moving the scene points around to match the model, then that makes this more efficient. It's not crazy, actually, to take a sign distance function and rotate it and translate it also, but I think this is more natural. Great question. Yes?
Previous slide showed me the loss function.
Yep.
They were all convex.
Good. So that's a good question. So are these all convex? Right? So the definition of a convex function is that if I take any 2 points on that function, that I could draw a straight line, and it would have to be, for a function, it would have to be above the function. Okay? So let's take the truncated least squares as the most extreme point. If I have this value here and this value here, then because the straight line between them is below the function, it's actually not a convex function. And this looks benign, and there are cases where, kind of like the low, all global minima are okay. There are some non-convex functions that are benign, but once you get into this space and you start adding them and shifting them and multiplying them and having multiple together, you can quickly get into things that have local minima. Great question. Yeah. So this one actually, the Huber loss probably is convex. Yeah. I think I have to look at it exactly, but that sure looks convex to my eye. But the others are not necessarily. Okay, so yeah, I think some of the more efficient algorithms for doing these sort of, especially tracking, will actually pre-compute sign distance functions for the different models and put them on a GPU. Okay, so that's nice. We don't have an iterative algorithm in the sense of correspondences, then implementation, but and then as SVD, we can write it all as one optimization, hand it directly to a non-convex solver, and get to some local minima using this kind of formulation. But so far, we're still in the space of objectives we already had, roughly. The real power of going to non-convex optimization and the real motivation to do that is to handle those non-convex, those constraints that I said weren't fitting nicely into the standard, our previous formulation. The non-penetration, the static equilibrium, and the free space constraints. So just as an example of sort of non-penetration, in 2D, let's say I have a bunch of scene points. Let's say I've just got a box that I'm trying to find. Okay, I've got a bunch of scene points like this. And I want to fit my model to my scene with my green chalk. I was looking for blue, right? But I want to say that my transformed model should not be in penetration. The box, I know, shouldn't be in the table. It shouldn't be in the wall. Okay? How can I write that as an optimization? I would like to think of it coming up with something that's like as close as possible. It's sort of trying to match the data, but it refused to go into the wall. Right? We could do the same thing we did before. We can say, let's do it with just theta in 2D here. So that objective maybe isn't so bad yet. But let's say I'm going to subject to the constraint that all of the model points, once they're transformed into the world coordinates, are, in this case, let's say it's 0, 0 here. Let's just say that they're greater than 0. So the x component is greater than 0, and the y component is greater than 0. This is a non-convex constraint because this is still, if I write that for all j, to flesh that out, remember we have it's still a function of my decision variables, and it's a non-convex. It's not a linear function in this case, but we know how to write it. This landscape is going to be not as simple as that cosine. I've suddenly added new constraints on admissible thetas and p's, but the initial picture isn't that crazy and isn't that different, and we can definitely ask our solver to do that kind of thing. Okay, and if you do, I did, and I got this, right? So here's my salmon red scene, my blue model. I drew the correspondences in, but so if I did an ICP sort of loop, but with that constraint, then I get a good solution out. Right? So once we go to this non-convex optimization, we can start writing rich constraints. What I said last time too quickly was that there are some ways to do convex optimization for this, for this type of constraint, and a handful of them. There's a world of trying to make the best convex approximations of these, which I'm a fan of that world, but it's a more subtle thing that I failed to make the point of last time. It's in the notes if you want. Okay, so how would you write this down just to make it sort of hopefully actionable, right? So if I had decision variables p, there's two of them in 2D, right? For my positions, my xy position, theta is one variable, and I can add my cost just like this. R, remember, is now a function of theta, so this is a nonlinear, non-convex objective. So I have to do it by, I can't say add quadratic cost anymore. I add a cost and I hand it a function, and then I'll add constraint and I'll pass it a function to do that bottom one. But those functions are easy enough to write. I just can say what's the position in the world. I take R as cos theta, sine theta, cos theta, and I compute it's just sort of the normal math, right? And then similarly at the squared, I can just call square, multiply the two vectors together in numpy, and mostly it'll just work. There's a little, crap about getting your variables into the function and out, this whole using partial and then unpacking with split. I'm not a huge fan of that. We'll make it better someday, but that's the tunnel that goes into the solver and then comes back out of the solver. So there's a little bit of boilerplate to make that good. Okay? And that's what solved the previous problem. And it can solve much more complicated problems. The generalization of this idea is, in general, you can say I have multiple models, or maybe the world is part of my model. It could be a function of the decision variables, or it could just be welded to the world. That's fine. Right? In general, you might say, I want to search for Q, the positions of my kinematics, such that the bodies match the points. You see why I think of it as a kinematics problem, right? And subject to the fact that there's no constraints. There's no collisions, no penetrations. Right? So there's a huge library of these tools that you'll build up on the kinematics pipeline. They're all doing something like this under the scenes, but they're calling the kinematics methods to make it effective. Right? So you can compute the signed distance of closest points between two bodies. That's queries that you can just ask the geometry engine for. And even better, you can just say, I want the distance between two bodies to be at least some distance, right? And there's actually a bunch of details inside there to try to make that good for solvers. The computational geometry of doing those queries is sort of subtle, but I'll talk a bit about it next week when we talk about simulation. But if I have two bodies, then already you can imagine that finding the distance between two bodies, the closest distance between two bodies, that's like an interesting computational geometry problem. It seems sort of manageable when I draw it like that. It gets worse when they penetrate, and you have to do the interior. Then the answers are not typically clean, okay, even for relatively simple objects. And in particular for a solver, if you have multiple bodies, okay, and if the closest point between bodies flops from being this body to this body, for instance, then that gives you, cost functions that can look, typically they're continuous but not differentiable, right? So you can have things like this in your cost landscape. And we try to do a lot of work to, that if it's at the minimum, that's one thing. It could also be on the way down to a minimum. It could do some silly things like this, right? These all make it harder for the optimizer to find its way to a good minimum. So there's hard work in the middle there that these functions do for you to try to smooth that out a little bit. Not enough to change your answer significantly, but enough to make the numerics good, right? There's a lot of details behind it. There's all open source, right? So you can look at it, but the difference between writing your own like this and getting it all right versus calling one that's been hardened a little bit is in all of these different little nuances. Okay, non-penetration, this example of bodies moving around and not being allowed to penetrate, is a classic example where you will have local minima. You sort of don't expect to have the nice picture of this. So let me try to make that point. So imagine, I got to get all my colors right. So I've got some scene points over here. Okay, my box is here. I have some part of my world here, which I'd say don't run into the table or the wall or something like this. And my current guess is of my model is over here, right? This sort of an optimization is going to try to pull it in here, and it's going to stop when it hits the constraint, and there's nothing powerful enough in the description we're giving it to suddenly change its mind and try something fundamentally different. And in general, even if your bodies are convex bodies, like the interior of the bodies are convex, because we're working in the space outside those bodies, collision avoidance constraints are the classic example of local minima in optimization. It's one of the multiple minima in optimization. Okay, so don't expect miracles. It's going to get stuck here. It's going to say, here, this is the best I could do. It's not going to pop over here. But when you're close, it can do wonderful things with complicated constraints. Okay, I mentioned three to begin with. I mentioned non-penetration, which I gave a very simple example of there. I mentioned static stability constraints. I'm going to talk about that more. You'll even do a problem set, I think, on it when we talk about the physics engine, because you're going to use some of the equations of equations of motion in order to write that kind of a constraint. But the last one, which I think is so important, and maybe one of the biggest reasons why the point registration problem, I think, is not sufficient, is that gaze constraint, the free space constraint, right? So, and I think it's so clever. So this is the free space constraint. So if I have my scene points over here, and my camera's over here, right? I guess I didn't get any returns over there because it's partial, it's occluded, right? Then I should immediately be able to say that any solution that's putting my model over here is a bad solution, right? It's not just that, even if it's close in the sense of getting those points close, it's violating something that I know about the problem, which is to have gotten this point from that camera, it must not be anything here. Okay, so there's various ways to write that. The one that convinced me first of how important this was used signed distance functions on a GPU to make it fast. And the way that they did it was they actually made a new obstacle. They turned it into a non-penetration constraint. So they basically said, I'm going to go ahead and make an obstacle. I'll call it my observation obstacle, which is not the convex hull. It's the body defined by the rays between my camera and those points. And they say I have a new body like this. I can compute the signed distance from that body on the fly and ask that the points in my model have a positive signed distance with that constraint. Okay? And I think that's just such an important cue that if you write an objective which says make my points match in a quadratic sense, you just can't capture that. In fact, even if you've only reasoned about point clouds, you've already lost that piece of information, right? The depth image, in some sense, had more information than the point cloud. The point cloud has thrown away where the cameras were, okay? But that is a hugely rich source of information to rule out a lot of possible strange candidates in the perception problem. And the folks that did that, I think, best, and the one that I learned it from, was this project called DART, which was trying to solve for Q. Is that playing? Oh, yeah, okay. They compute these signed distance fields, right? That's a visualization of the signed distance function. And they do it for each body, and then they search over Q, and they make these incredible demos of even tracking real people's hands with an approximate model of a hand, where they're just using this basic idea to solve that problem, subject to the kinematics constraints. We're using theta instead of pose, non-penetration constraints, and free space constraints written as non-penetration constraints, all with signed distance functions. I put it in the middle because I had some cool visualizations of the optimization at work. Fast forward here. Okay, so when you're seeing that, what are you seeing, right? You're seeing the solver take an initial guess. It has some Q. It's somewhere on the landscape, and it's walking down the landscape, and it's slowly snapping into place. And they just did incredible tracking demos with this kind of work. Even tracking humans. Super impressive. It can get, okay, so the property of these algorithms are that if you start with a good initial guess, it can snap in. But if you just think of this as like in the context of this demo, you actually saw it lost the arm for a second. Did you guys notice the frame where it lost the arm? So if it gets confused, then it's sometimes very hard to get back. So these things will work incredibly well until they don't, and then they fall off the rails. So don't put it in a safety critical application, maybe. But they're super powerful, okay? And that's an example of using it recursively to solve the tracking problem, like we talked about. So we took the initial guess, we found some minima, and then we took a new snapshot from our camera. The problem data moved a little bit, but hopefully the minima didn't move too much, and we just keep solving and it's trying to track the moving minima in the landscape.
So is each of these limbs using different tracking methods?
No, the limbs are all using the same tracking method. The comparison is I think only one of them is visualized in that. Yeah. So the parameterization is Q, which is like the generalized positions, and it's just searching through Q in order to solve those. Okay, so that was that's the sort of the importance of non-convex geometric reasoning in there. Like I said, there are more advanced topics in geometric perception. For instance, I really like the convex relaxations, where you try to find versions of the hard problem that you can solve very reliably. I put a very simple example of one in the notes. I think this notion of tracking gets into a nice set of different tools where you can solve the tracking problem differently than you'd solve just the one-shot perception problem. Like I say, you can use differential kinematics instead of inverse kinematics. So, dynamic, and dynamic obstacles, if you will. And I would say dense reconstruction is also a nearby problem here. If you wanted to build a map of the world or build your object model from just having a camera moving around it, these two both are sort of, you might have heard of SLAM, simultaneous localization and mapping in robotics. It's really based on the same foundations that we've talked about here. Very dependent on getting correspondences correct, but hugely powerful and important and successful applications of these. So if I just reflect back on sort of what we did and where does it fit in the space of manipulation tools, I think geometry is incredibly important. I think our depth sensors are superhuman in their accuracy, for instance. So in terms of refinement of an initial guess, they're incredibly valuable. But I remember a few years ago when we started doing more work with deep learning perception, and we were using RGB as much as we were using depth. And that transition sort of happened where we started using the color values, handing them to a neural network. And I remember asking the guys in the lab, I said, okay, if you were to give away either the depth or the RGB, if I can take one away, which one would you keep? And that answer flipped. And I think nowadays, if people have to pick just one, they would say, take my depth, give me my RGB. Because there's so much value, there's so much information that is not captured in the XYZ value of the point cloud. Context about, when objects start, when they stop, but also much, much more than that. We haven't talked enough about RGB, but we will. Okay. I do think that it's very natural to combine guesses based on data-driven methods, and RGB, and then refine them with the geometric methods. And I think we learned a bunch of cool geometry stuff. Hopefully it's good. Okay, see you next time.